Hello, everyone. Welcome and welcome back. And it is my pleasure to introduce our next speaker of the day. Next up, we have Stephen Wong, and he is the Chair Professor and Chief Research Informatics Officer at Houston Methodist. And his talk today is entitled AI in Precision Diagnosis, Case Studies in Cancer and Stroke. Please welcome to our virtual stage, Stephen Wong. Okay, Stephen, you can join us here by turning on your camera. Okay, great. Hi.
Yeah,
Okay, and whenever you're ready, I'll just turn off my camera and you can take it away.
okay, I can get started. I need to share the screen, right? I'll just turn on the...
Yep, you can share your screen.
You can see the PowerPoint?
Yes, if you can make it full screen, looks good.
Okay. Let me have a... Okay, can you see that? Hello?
Yep, looks great.
Should I just start it?
Yep, go ahead. You're ready to start.
Yeah, thank you, Morgan, for the introduction. I'd like to share with you today some of our work in convergent AI on the precision diagnosis medicine. I'd like to give you a couple of case studies to get some concept on it, and I picked cancer and stroke with other application. I think these two exemplify some of the things we want to discuss. This is kind of next generation clinical AI should go, not the current you can buy it on the off the shelf, and something that is coming. So first thing is we may ask a question: why we need a healthcare transformation right now? It's really the pressure point is really three things, right? You think about it. You have a low cost, high cost, low quality of the medical system we have in our system, and in the macroeconomic side, because government put a lot of badges try to fix the problem with regulations and drug pricing, payment, outcome, all kind of thing. Actually, sometimes it may have a different effect, causing more paperwork to be done. But macroeconomic is a pressure point. And socioeconomically is a patient as a consumer concept, and we have more chronic management patients, public health, population health, especially today in the pandemic. Actually, the need for the telemedicine, tele-diagnosis is more than never, you know. So all these things really driving the acceleration of the healthcare, if that's the case that you think about it. And and if you look at it, one of the topic, these are very complex topic. I like just assuming one area, the driving thing is really the cost. And we spend about $3.7 trillion. And I think the cost for the waste by different account is about $760 billion to all close to $1 trillion we wasted on healthcare. And this is the part that I think a lot of healthcare can be done. This is a more detailed breakdown and administrative complexity, pricing, especially drug pricing, fail to care, and overdiagnosis, overtreatment, fraud. Although it's got a limelight to fraud and abuse, actually it's not as much compared to the others. Care coordination, as I say, the population outside the hospital. And given a limited time, I'd like just only point out two things. I want to each pick an example about how the care failure costs a lot, and also the overtreatment. First case I want to give you is a breast cancer. And this is graph which exemplify the issues. The mortality rate in the last 30 years actually haven't changed much. In fact, it's decreasing. The drug is better, the treatment is better. But at the same time, the number of incidents increasing. You wonder why, right? Because the mortality incidence should go parallel. And if you look at it, during around in the early 80s to 90, close that decade, we start introducing mammogram screening. And so actually, this increase in incidence come together with 30% increase of the widespread mammogram screening. This is has been persistent even today. If you look at 24 million cases we have in mammogram in this country, and we about 10% false positive, but you look at particular category, BRAF4, which actually we have a wide range of 55 to 85 false positive. And that's cost country in estimations about $3 billion, just overdiagnosis and downstream cost. And one more thing is really effect of the people, the false positive diagnosis causing anxiety to women, and actually sometimes no esteem, no self-esteem, in the sense that they find out they do biopsy and turn out nothing. Some people don't trust the result, and so also a psychological barrier, not just cost alone. And how to address this issue? In the case that we created a breast cancer risk calculator, and which is basically input feature, AI, give a score, and recommendation, very straightforward. And we take advantage of current digital architecture. You have PACS, your electronic medical record, your raw data somewhere, comprehensively in most hospital centers these days. And we pull the data for, in this particular case, we look at BRAF4. We pull the case of mammogram and ultrasound. And then we do image features analysis. And then we do the free text report, EMR, and also clinical features. So we took all this information. This requires some natural language processing. This requires some sort of medical image analysis, combined it together into a database called Imaging-Omics. And then we're using deep learning risk assessment, create model. And this is the result. We've done about 14,000 BRAF4 category breast cancer patient cases, and over the last 10 years in Methodist data warehouse. And we also use 2,000 of them for validation data set. And our next door neighbor, MD Anderson, give us about 764 for cases. And this is a preliminary result. 3 different type of medical institution we engaged, not just Methodist. We also have MD Anderson, UT San Antonio, and this category. These are the validation data set, about 4,000 of them, and based on tested on the model we trained using the convergent AI I showed you early on, the calculator. And this is the Methodist data. And one thing is we want to keep sensitivity 100%. That means we don't miss anything. It's a first criteria. And the specificity actually 71, 68, and 77, which is excellent. We actually reduce unnecessary biopsy by 70% if it's a further validation is good. One thing about AI is, especially in the medical area, most of the time you really don't have clinical data in completion. So you are missing some information. So when you build an AI model, it has to be robust, and it has to be robust in a way that you can deal with some fuzzy data or missing data. So in our case, we around calculations of within 20 percentile missing data or the parameter we enter. This clinical, this breast cancer risk calculator still works. And this is one example. We put it on the risk calculator. In a sense, an app. People can input the parameters. Some of them are imaging features. Some of them are demographics. Some of them are just patient history, insurance. And all this information put in the cloud, calculated, and get back the result very quickly, almost instantly. And it gives you a parameter, indicator whether you should be okay, borderline should consider biopsy, and definitely should go for biopsy. There's further division of the BRAF4 category, and this is the whole concept on how to using AI to kind of integrate the existing raw data, adding values to be a more intelligent calculator, to improve the current standard, which is BIRAC, breast imaging radiology standard, which is based on that do biopsy. And this kind of situations, phenomena is not unknown in breast. In fact, you can look at it. One thing I want to mention, AI, one of the major problem, AI is very black box. People don't believe in it. So you want caregiver, clinician to use it. You have to think about how to make it more transparent, at least a clear box. And in this case, we put all these parameters open. These are we train 100 and then we filter down to 22. And this parameter, when you give it to oncologist or radiology, they look at it, it makes sense to them and gain the confidence for them to use it. And this is a very good consultation tool for them to discuss with patient also. So in this one, we can cut down 70% unnecessary biopsy in BRAF4 patients. And it's not just save a cost, really psychological well-being. And as I say, this type of over-screening of cancer, especially area, is not alone in breast, in lung, in thyroid, in prostate. That situation is in the past we don't have enough big data to kind of improve the kernel index, but nowadays seeing the EMR, PACS, all these raw data form is already there. I think the AI technique can take advantage of them and quickly improve the index. So the whole array of opportunities really using AI, integrative AI, to reduce cost and actually reduce waste and do no harm to patient. More important, every time you do one unnecessary procedure, you never know what the downstream effect of the patients. So this one example on the over biopsy, over diagnosis of top on the ways in the country, the AI can help, the kernel can help, and not many tools available right now, but the basic data are there. I think the next generation, you will see a product coming on, not just for breast, as I say, for different type of organ. And the other one, the other case study I want to show is about stroke. Stroke is the number one cause of disability in the United States, number two death in worldwide. So in our countries, in United States, about 800,000 stroke cases, incidents per year. And majority of them are ischemic stroke. Asia tend to be a little bit more in the hemorrhagic, but because of diet, actually recently, a lot of, like Japan is almost similar to US already, up 80,000. One thing about stroke is interesting is stroke actually is treatable. People think about stroke is untreatable. Not true. We have tons of techniques, all kind of advanced techniques, drugs, treatment, intervention. Then you can treat patient with stroke. So what's the problem? Then you ask the question, right? How come we still have this issue? If you look at this pyramid, tip of iceberg, you understand. We have suspected strokes about 800,000 per year. And we have this primary comprehensive center take about, treated about 1/3 of them. Primary care center is about half overall US. And reality from anatomy that we can do on the patients when we identify stroke is about 10%. And really are missing a lot. And in fact, we're getting even more so-called silent missed stroke, which is the majority of the population, 50 to 98, depending which paper. But even the most conservative, more than 50% population, silent stroke, we don't able to detect it. And the purpose of AI or stroke care is really moving this silent stroke into suspected stroke. And for suspected stroke, you go to something you can treat like from anatomy or TPA. And this is the trend we should do it. But to do that, you need to catch it first. Although there are tons of treatment, diagnostic detection is an issue here. And if you look at that, CT is most popular in the clinical site. And the question is, CT has a certain problem in the sense that they have very low detection rate, and they only detect about 30% less than 3 hours, and it won't detect the infra until it's very large. And in most clinical ER room or outpatient center, the CT is around contrast CT. That's very noisy imaged. In a noisy image, in a rush hour, you try to figure out what's going on with the patient. Very difficult situation. And also, in reality, this country, we don't have enough stroke specialists going around in the community hospital, rural areas, or even ER. We have one or two stroke specialists cover the whole 8 hospitals we have in Methodist, even in a major medical center in Houston. So Diffusion MRI is a gold standard, and it's clear. And the problem is, is mostly 99.9% you don't find the ER room because it's too expensive to maintain. It is after the patient administered into hospital, then you use a diffusion MRI to confirm it or to check it. So it's not useful. It's after the fact things. So ER provider go stroke call. Okay, tendency overcall in this country is overcall with 30%, miss with 20%. So roughly you can count, right? It's about half of them are wrong. That's what the current state of the art in the stroke care. And so the idea is really, can we leverage AI to look at the stroke detection, so we can have give to the patient at right place, right time, without missing anything. One approach for as I mentioned, the first issue here is really about the denoising. CT, non-contrast CT is very, very noisy. So how you do it, and we put the data, we apply to a deep learning, we're using a unit, a modified unit, rotation reflection equivalent unit. And we're using a group, and using that to denoise the normal range of the CT scan, which is currently has no product doing that in that sense. And we have a longitudinal data, so we have different time point of CT, and pull out from a data warehouse. We train using this model and denoise the CT. And this gives you example. In fact, this is this case on the stroke case. You can see the original long contrast CT compared to the one using AI to denoising it, and you can see clear. Now I circle it. You probably see very clearly. In fact, this is a missed case stroke. We put it out, and the ER doc actually missed these stroke cases, and we compare that with the MRI, and which is a gold standard, which is you can light up different things, but you can look at it. The contrast is very good. This is one approach to doing that, and we also any complicated problem is not solved by any technique. So we are doing another way. As I mentioned to you, MRI is a gold standard, but you don't have it in ER room. So what do? We have gazillions of MRI of patient in the hospital. We're using MRI to train the CT, and exactly what we do using AI. This is a quite interesting. It's a cross modality AI training, and using based on certain concept of medical physics, since we are interested in gray matter and white matter in this case, and it works very well. And this is the result. And MRI, the ID case. So next time, and we are in the middle of a clinical trial on this one. The CT trial, we already almost finished the clinical trial on denoising, but this one is in the middle of it. The idea is very simple. Is once we create this early detection map, and we can actually CT show up. We can embed it ADC. This is one thing to identify stroke automatically, generate from CT, and this whole concept. Now this is the imaging side. I don't know if you guys. This is no more. This sitcom is no more there. It's called the Good Place. That is a AI assistant, right? Called Janet. It's all knowing everything. It's nice everything. You ask anything, you have an answer. It's a fantasy comedy. But thing about it is, if we can provide Janet equivalent in a stroke center or in the ER room, then you have the facial information, speech, image, body movement, and the Janet will tell you what the patient has stroke or not stroke quickly, right? Even without a doctor at the moment. Yeah. So this is really about create a kind of the intelligence avatar. In this case, even your personalized one, because the more you learn about it yourself, they learn about your pattern and detect it better. And you can look at many techniques to look at it. The current pattern recognitions, voice recognition is achievable in this area. And this particular case, in the stroke area, the devil is the detail. And those are genetic technology. How you adapt the technology to solve a particular big problem in medicine, in the disease problem is not easy. And I show you the denoising CT. I show you the MR CT, cross-modality mapping, this imaging side. And this one actually, and normally for the stroke patient come in the ER room, or clinical center. We had them read some story, and it's a famous cookie jar story. And based on how the patient interpret the image, how they speak, the language they use, the abstraction they used, and we can actually identify the patient with a stroke. Sometimes a speech pathology even can tell which area of the brain they have a stroke. And this technique can be automated using speech recognition type of technique these days. And this particular, I'll give you an example. This is one of the clinical coordinator. She volunteered for the job.
In this picture,
she tried to simulate a case of a stroke patient. And there's a normal case.
Overflowing onto the kitchen floor. She's wearing.
She read the story. She cookie jar story, and try to interpret
it. Looks like it's daytime,
and then you notice that we also at the same time checking her facial microsegmentation of the face, the mouth, the teeth, and I mentioned earlier.
In the cabinet, the boy is on a.
If you look at case, this is what she simulated.
In this picture, there is
Why do you stop this?
There's some kids.
She saw enough patients to understand how they behave, so simulate quite well. The language they used, the pace they used, and stimulus response. All these can be interpreted. Right now, it's very subjective by speech specialist or Yao dog who is untrained. But this can be completely automated. And this the vocal speech analysis. That's what we do in the model. When we use one of the AI model to do it.
In this picture,
and this is on the voice side. The other one is the facial side. At the same time, stroke patients. And we are interested, by the way, we are not interested big. You see a lot of cases out there, big asymmetry. We're not interested in that. Those things you don't need a machine to tell you. Even a lot more untrained nurse can tell you. The majority of stroke, the common detection are very subtle. So in this case, 80% of them are very subtle, how you pick it up. And that you need a very well-trained personnel in order to detect it. And this one, we're using a 3D facial video stroke detection and using AI technique that we are doing that. This will be publishing. This is a flow chart on this particular one. So all these techniques, I just mentioned 3 techniques, right? You have imaging, and then you have voice, you have the face, and eventually you will do a Janet type of thing. This is one of us a prototype. We are still doing that.
Please keep your head still and move your eyes to the right.
It's done with one of our MD PhD students.
And then move your eyes to the left for 3 seconds.
The training on that. So there is a set of procedure that people detect you. The neurologist will go through and identify whether the patient has stroke or not stroke. And you have an avatar to tell them to take the actions. And at the same time,
to your face
automatically acquire their voice and their facial recognitions and analyzing it and movement, give a score, right? The teeth movement, the ratio, all these things can be automated.
Keep the camera pointed to your face and use the other hand to touch your nose 3 times.
So this type of automation you can be done with the AI technique. Currently, there's no product in this area, but it's an interesting area. You can see applied to many choices. And to save time, I just want to move forward a little bit. You can move different hand, different protocol. And something that we can also calculate, right? You can have patient
hold your right arm still for 5 seconds.
Hold the arm for a couple seconds.
1.
And then we can start measuring whether you're still or give you a certain score or something like that. And we take the other arm and give it a gyro score again. And you can do walking, all kind of things.
Hold your right arm still for 5 seconds. And 3, 2, 1.
And you can see that all these technique, if it's working, we are right now, we try to do it is in our ER room setting, but eventually you can think about this thing can be loaded on the cloud, and patient at home suspicious, so they can log in the system, and then their family member can help, or even patient for not very serious stroke, they can actually test it themselves.
Walk forward in a straight line in 3.
Okay. So this is a preliminary result we have done. We do the testing. It was about 47 male and 37 female subjects. And then we compare the result, actually. we compare with ER doc, okay, directly. Remember, ER doc also have clinical impression and CT scan at the hand to make a decision. But ER doc is not trained as stroke specialist. Our accuracy actually is just looking at the fusion, combine the video and audio. We got about 80%, 79%, above the 72% accuracy of ER doc. And of course, the gold standard we compare, as I say, is the diffusion with the MRI I mentioned earlier on this particular part. So I give you an example that we are ongoing, right now we are ongoing trial, but this is just give you an example that how AI technique is beyond now just individual. AI technique actually affecting the clinical care. And with the clinical care, you can look at it, you can just improve. In this particular case, you're not just improve the accuracies. Actually, you actually release the burden of stroke specialist or doctor to do something that more urgent. And sometimes there are many things you can think about imagination, but the technology is there. How to integrate these together to avoid misdiagnosis in this particular case. Stroke is one example, and stroke is very timing, is very everything. Accurate timing is very everything. Very different for Alzheimer. If you diagnose Alzheimer, what can you do? You know, questionable. But stroke is something. Is time is everything. So this is a very important example. This is what the converging AI, different AI technique can do together for you. I'd like to wrap it up a little bit. I just give you two cases. I'd like to thank my group of people, and in my group, my cancer center in this project, and Methodist Stroke Center in another project, and also our labor, MD Anderson, and also San Antonio, and Penn State. One of my former colleagues and students actually also help together, and the funding support. Thank you very much. That's all I have. If I don't have any questions, I'm done. Morgan. Yeah. Hello. Yeah, it's very video sound, very hard to hear. Sorry. Let me see. I have questions on. Is the law function? What are the two terms of K1 and K2? Let me look at it again. I think this is a paper we're writing it up. This is customized function, and it's a customized function. We do it empirically, identify it. Okay, so in fact we have a pattern on it right now, filing on this particular one. Another question is the AUC value when the CT stroke prediction. AUC value for CT stroke prediction when compared to MRI as a gold standard. Yeah, we haven't done that part actually. Right now we are doing something different. We look at the mean qualitative value. We are writing up